What you are looking at are the Christmas decorations that can be seen every year at the Peru Utilities Power Plant. This will be the last year the community will be able to view these decorations. Shortly, demolition will begin on the power plant after more than 50 years in existence. Good evening and welcome to another special edition of Miami County Monthly News, where our goal is to bring you positive news stories about Peru and Miami County, Indiana. This special edition is about the Peru Utilities Power Plant that is set to be demolished beginning in 2017. The plant hasn't been used in the last 3 years. Miami County Monthly News has always been curious about what the plant looked like on the inside and how the plant worked. We thought our viewers might be interested. Also, before the plant was taken down, we reached out to Peru Utilities and we were fortunate enough to be invited on a tour by Joe Pandy and Joshua Chance that was given to Peru Utilities board member, Dr. John Crawshaw, and several of the City of Peru department heads. Thank you Peru Utilities for the tour and allowing us to get video.
All right, we're here with Josh Chance, who is the project manager at Peru Utilities, and we're getting ready to go and look inside the old power plant with him and Peru Utilities General Manager Joe Pandy. And Josh, can you just explain kind of through a diagram what we're going to see when we get inside the power plant?
Sure. Basically, we bring in coal 2 to 3 inches in size, and we put it in our coal bunker, and we take it in and we grind it up into pulverizers into a fine talcum powder, baby powder type size. We push it into the boiler, which is the tube that has tubes in it that are filled with water, and we burn it as it goes through the boiler. It boils the water. We turn that into steam, and we put it into the turbine at high pressures, 800 pounds, 1,000 pounds of pressure, and it turns the turbine, which turns the generator. And then the steam itself comes down and condenses back into water, and we pump that into the system, and we condense it back into water by pumping river water from the river into what we call a condenser, and it cools things down, and then the river water goes back into the river and
Safely goes back into the
river.
It's not touched anything but pipes.
That's correct. And then the steam goes back into the boiler and gets heated back up instantly right again, and then we reuse what steam we have. And then the pollution, the warm air goes out through the stack through our pollution controls.
All right. So when we get in there, everything was designed originally on different levels, so to speak, because of the process.
Right.
So the turbine's the highest point, basically, or does that matter?
The turbine doesn't really matter. It's just based on where your steam outlet is from the boiler.
Okay.
It's most efficient that way.
But it's designed basically like this process here to make it most effective.
Very close, yeah.
Yeah. All right, well, let's go check out the inside and see what it looks like. And I appreciate you guys taking the time and showing us.
You're welcome. Let's go.
All right, thanks. So this is where the coal was delivered?
Coal was delivered into these bunkers and then conveyed by conveyor belts up into the plant.
Pollution controls, oversized.
So if you take the big unit here, 22,000 kilowatts, it could burn 22,000 pounds or 11 tons of coal per hour.
Wow.
11 tons of coal per hour. So the coal was coming in by truck at 15, 20, 25 tons, 20 tons per truckload, and this unit would be burning a half a truckload every hour of the day.
So it was a continuous thing. It was feeding it.
Yeah,
15 to 20 trucks a day. When we were doing both of them, 15 to 20 trucks a day for both units.
so they burn less at night, more during the day when they were used. So this silver box is the precipitator, Environmental Elements Corporation. That's the dust collector that all the smoke coming from the boiler goes through that and collects the particles out of it, and then they're put into that silo and dumped out. Pull a truck in there and dump the ashes out, and then take the ashes to the landfill. Walls, and the coal that's going in there in chunks is being agitated with those steel balls to break up the coal into that face powder consistency, and then it's blown up to the furnace where it's blown in to the 2,000 degree combustion zone and instantly flashes to fire, you know, to burn.
There's about 12 tons of balls in here, 10 to 12, depending, and they're all different sizes from 3.5 to about 3/4. And believe it or not, the friction of that will actually wear them down to, we'd have
No
to pull them
kidding.
out.
Solid
back
steel
in.
balls?
Oh yeah, and they're heavy.
Yeah, two of everything. So in case one breaks, you can still run the plant with maybe at 70 or 80% capacity with the backup unit. So everything's redundant, 2 pumps, 2 fans, pulverizers, two of everything per unit. And then the condensers look like this. So the cold water from the river is on the outside of the, or is on the inside of the tubes. You can see all the ends of tubes on the tube sheet. Cold water going through and steam coming down on the outside of all those tubes, creating a vacuum, sucking the last bit of energy out of the steam. So the cold water contrasting with the hot steam is what created a vacuum. And if during the summer you got a lousier vacuum because the river would warm up. So the best conditions for efficiency would be in the winter when the river water's really cold and you suck more energy out of the steam. Out, it gets the salvage value, which netted our price to be lower because those tubes are an alloy like copper, nickel tubes or some kind of exotic metal to stand up to the corrosiveness of the river water and the hot steam striking them. And so there's value in that metal. There's value, of course, in the steel piping, the copper in the electric lines. There's all kinds of metals in here, but there's also all kinds of chemicals. Probably everything is painted with lead paint. The boilers are insulated with asbestos, which has to be abated. That's $500,000.
Is that the only part that has asbestos is the boiler comes out?
Oh, that tank right there,
Piping, that's
it's encapsulated
asbestos, right?
asbestos.
It's all asbestos.
And asbestos is legal if it's already here, you can't come in and put it back in, as long as it's encapsulated, it's non-friable.
Right.
The worst part about, you know, people saying that maybe we don't want to knock this down is that this asbestos is sitting here. And if we have structure failure or whatever, that becomes friable to the environment.
Right.
And
If we wouldn't maintain the building and rainwater comes in here, then you're gonna be washing chemicals out to the river. There's a lot of environmental issues here. They brought in an expert environmental consulting firm and they estimated it was over $100,000 a year just to keep the thing mothballed, just to keep it from falling apart and falling into the river. So I believe that's why the board decided to tear it down. 1,000 pounds per square inch pressure. To fight the pressure of the steam in the boiler, they've got to force water into the boiler at that 1,000 PSI. So they're obviously very heavy industrial pumps. And of course you've got various gauges and
They are.
circuit breakers. These are like the circuit breakers in your home. So here's the pulverizer breakers, mill breakers, the coal feeder breakers. So a plant like this would typically use 5 or 6% of what it generates just to run itself, to run all the motors and grinders and fans, what we call a parasitic load, the load that doesn't get out to the customer is consumed in making the electricity. And then these boilers, they go up just the whole height of the plant. So this is the boiler itself. And it's got behind these, this jacketing, the steel jacketing, it's got asbestos insulation, and then the tubes in which the water is turned into steam. So they're typically 8 to 10 stories tall, you know,
we had it down.
anywhere from 80 to 100 feet tall of steam generator.
How many employees did it take to run it, the facility when it was up and running?
18.
18 employees a day?
18 for the week.
For the week?
24/7. If we went 7, we wouldn't go more than 2 weeks at a time, but 7 days a week. But usually when we ran, it was 5 days a week, and it was 18 employees. And they were trained in everything: maintenance, coal handling, ash disposal, janitorial work, and operations.
Okay, it's the first time I've had a chance to do this, but how many years have we been doing decorations?
I can't answer that. A long time.
I'm missing the one up top. Didn't they have one all the way up top?
For quite a few years, we had like a Christmas tree on a homemade pole up there.
Yeah.
We would climb that, and it's gotten to the point where it's just the last couple of years, it's
Yeah.
really unsafe.
So this is what's on the inside over here. I'm gonna get this.
So this would be where the head operator would be, who'd be controlling the boiler and the turbine generator and the electric output going out. So you'd see different circuits going out to the station itself and different substations. So this is all electrical controls. And there's an exciter, which is a generator of its own that creates an electromagnetic field to excite the alternator that's generating electricity. So you have to start with exciting the electromagnetic field. It's an electromagnet with a small generator, and then the big generator starts producing the power that goes
When
out.
the power's generated, it's a DC, and that exciter
Oh, it is?
to AC, yes.
And
Just
so,
like your alternator on a car.
Wow.
so this would be a typical operator position. When everything's going right, you'd be sitting here, you know, look at the computer, look at the magazines or whatever, have your lunch. And then when things start to go wrong, everything in the place lights up all at once. There's an enunciator of alarms. And then you've got to be what they call it in the industry, assholes and elbows. You're just flying around trying to get things under control because you've lost your exciter, or you've got a mill that's plugged up with wet coal, or you've lost a feed pump, or whatever's gone wrong. It'll all go to hell right now. And you've got a few minutes to recover.
Did that happen often?
Yeah, from time to time, yeah. Yeah, I mean, everything is dependent on something else.
Right.
You know,
So
your pressure is dependent on flow, your flow is dependent on temperature. I mean, everything's dependent on something else. And when one thing goes wonky, it's like a butterfly effect.
You control the amount of electricity by the amount of steam you put into the turbine. So this is, you know, these would have to be overhauled every 5 years or so. You had overhead cranes, and the only way to take the machine out of the building was through these overhead
I remember
doors.
them setting cranes up there.
Yeah.
So what would that entail?
Oh, it'd be a month, 6 weeks of work by skilled mechanics, 24 hours a day. You take all these covers off, lift the turbine out with a crane, and take it back to General Electric in Schenectady, New York or somewhere to overhaul it. Because the blades in there are, you know, some of them are yay long. They look like the blades in a jet engine. The alternator, just like the alternator in your car, that's spinning with an electromagnetic field to generate electricity. So the electromagnet that's spinning is the shaft inside this casing. And then around it, there's like a donut of wires that's called the stator. The spinning magnet's called the rotor, and it's getting its electromagnetic charge from the exciter. So the exciter is putting a charge on the magnet, the turbine's spinning the magnet, and creating an electric induction field of alternating current out of the generator. We have 3 phase. There are 3 different.
So we're here, this is your turbine.
It's 12.5 turbine.
This is your turbine, one of your turbines. And then down here is your, what'd you say? Your
Steam condenser.
Steam condenser.
Yep.
And how does that work?
We pump, I think we can get up to 10 million gallons a day out of the river, out of the Wabash River, and it comes into the plant here and underneath that turbine. Comes through into copper tubes. I think they're 20-something feet long copper tubes. And the river water goes on the inside of the copper tubes, and the steam hits the outside of the copper tubes. Copper tubes become cool. The steam becomes water, rains back down into what we would call a hot well. Gets pumped out of the hot well back into the system.
Is that this here?
Yes. And then the river water on the inside of the tubes touches pipe and more tubes, and then goes back out.